Okay, so last time we saw what a computational problem is, right? If you remember, it's all about language, language over strings, formal language. So again, what was the problem? So the generic structure is that some alphabet will be fixed, and then the problem will be encoded by language. And the problem essentially is that given any string, decide whether this string x also belongs to this given language. Okay, and we said that for a particular x, the question that is x an element of L, so this particular question will be an instance of the problem, right? The problem is to solve this thing for all x, and the answer is yes or no. That is why it's a decision problem, and we gave some argument why we concentrate only on decision problem. So now the point is how to do that actual computation, how to decide that answer and whether it's yes or no. And so far we have established our formalism to encode the input, and the input is string over suitable alphabet. So similarly, we have to set up some formalism for the computer, whatever is happening here. So today I'll just mention all the models of computation that we are going to cover in our course. So today's lecture is just about an overview, and I won't give rigorous definition or anything. So we will just name all the different models and what are the relationship between them, roughly some hierarchy between them. So and this model of computation, so this we need to describe formally using some mathematical notation or something. And once we have our model, so what will that model do? So it will take input and it will somehow encode some kind of behavior, how this computer behaves given this input, right? Now after we see how this computer is behaving, we should be able to tell whether the answer is yes or no. Okay, so you may say that okay, the computer will somehow give an output yes or no, but it's not really that. The computer will somehow react to the input, and depending on how it can react with this input, so we need to set up some criteria to decide whether we interpret this behavior as an yes or no answer. Okay, so each model of computation will have an associated acceptance criteria. Okay, so we will see all this when we study specific models. So far all the discussions are kind of high level. So again, this model of computation is just a mathematical or abstract model of some kind of computer. It takes inputs which are strings over suitable chosen alphabet, and each model has some associated acceptance criteria. Okay, and what is it again? So the model will somehow react to the input, and this acceptance criteria determines whether we interpret that reaction as yes or no. So we use this jargon, accepted by a model M. So a string x is accepted by a model M if the answer is yes for that input x on M, right? Similarly, if it is not accepted, we say it's rejected. So these are standard terminology to say that the string is accepted or rejected. Just remember that. Now this is about a string being accepted by a machine. So then we define the language accepted by this model M. So what is that language? It is simply the set of all strings which are accepted by M. Okay, so X is a string. If you take a set of strings, that we call a language, and here the language is the set of all strings that are accepted by our model. Okay, so and if we denote our model by M, it is kind of customary to use this notation L of M to denote the language accepted by M. Sometimes we change it, but mostly we will use L of M. So to solve our computational problem, so what was the computational problem? Given L, you decide for all X whether this X belongs to L or not. To solve this computational problem, so we are supposed to construct a model, okay, M, such that this L of M is L, so this L, right? So that means you are given this problem, so for a particular instance X, so you treat that X as an input to your computer. You feed that input, see how the machine behaved, you interpret the answer according to acceptance criteria. If it is yes, then you say that okay, answer to the problem is yes, otherwise you say no. Okay. So this is how you solve the computational problem using this sort of mathematical machine. Now, two major categories of these models are automata and grammar. Okay, so they are categories. So inside automata we have many different kinds of automata. Inside grammar we have many different kind of grammars. So these days we mostly concentrate on these two formalisms. There are other formalisms like lambda calculus and recursion theory, but we will not cover that. In fact, we will also show some equivalence, and it was shown that these models, this lambda calculus, recursion theory, they are equivalent to a kind of automata, say, called Turing machine. So that is part of Turing's big work, and it kind of proved that all these seemingly slightly different notions, they all converge into the same thing. So that thing is inherently of some value. I mean, it's like no matter how you try to come up with a definition, you finally end up with something which is equivalent to everything. Okay, so what are automata and what are this grammar? So automata are more like machines, and grammars are like rules, like grammatical rules. So as I already said, so these are kind of mathematical, abstract and ideal machines which read the input string. So input is always a string, and it reads the string symbol by symbol. So you can think of the machine acting in discrete time steps. Okay, it's a discrete sort of machines. At each time step it is reading one symbol, processing it, and then moving into some new symbol. So one after another it will read all the input symbols, so it will read all the input, and at each step it will react somehow. After reading the symbol, it will somehow react. In fact, later we will see that in a time step it may not read a input symbol and still react, but anyway, to keep things simple for the time being, say this is our picture. And there are many different kind of automata, and we will put most emphasis on finite automata, and later we will see push down automata, and then finally Turing machine. So linear bounded automata is not that important. The main important parts are finite, push down and Turing machine. And at the end of the course, maybe we will see that this Turing machine is the model for all-powerful computer. And so this finite automata and push-down automata, they are kind of a restricted type of model, computer with some limitations. But this Turing machine is the model of computer which has no limitations at all. So again, the whole thesis of Alan Turing was to prove that if you can computing anything at all, then you can compute that with a Turing machine. Now, there are two versions for each of this automata, and this is very important. Now, as for a machine, you think that if you give it some input, it will behave identically on identical input, right? You give some input and it does exactly the same time always. Exactly the same thing every time. So now in our mathematical model, deliberately we will consider other model which does not do that. So our usual notion of machine is that it's something deterministic. So the behavior of the automata is completely determined by the input. Okay, so if that is the case, then we will say that our automata is deterministic. So as I was saying, at each time step you are reading some symbol and something happens inside that machine. So whatever happens inside that machine, it is completely determined by what it has read as input, right? So if that is true, if it is indeed completely determined by the input, so then we say that it's deterministic. And in some model, we will see that even when you give it the same input, it can react in more than one ways. Okay, so so it can react in more than one ways on the same input. Okay, so the behavior of the machine or the model, it is not fully determined by or it's not uniquely determined by the input, right? It can, upon reading an input, it can do either this or that. It's kind of it makes a non-deterministic choice what to do. Okay, and this behavior is called a non-deterministic behavior. These automata are called non-deterministic automata. So for each of this model, there will be this versions: this deterministic finite automata, non-deterministic finite automata, deterministic push-down automata, non-deterministic push-down automata. Similarly for this LBA and Turing machine. Okay. Now, to give you some more detail, still we are not giving any rigorous definition. We are not there yet. We have to define many things before we reach the definition of, say, finite automata, deterministic finite automata, non-deterministic finite automata. So here is just intuitive sort of way to represent this finite automata. So this is a deterministic finite automata. Now think of this as a machine. Okay, this machine behaves according to these rules. Okay, so these rules. So this machine starts in state Q0. What is a state? I'll not define right now, but somehow say the machine kind of goes over this picture and this Q0 is just one of these circles. Okay, for the time being. So it starts with this circle Q0, okay, and it reads input, and the input symbols are either 0 or 1, okay. So this 0 and 1, this 0, 1, so this corresponds to the input symbol. So say this 0, this 1, okay, and starting from here it reads the symbols one by one and follows these arrows accordingly, right? So this is the behavior of the automata. Now we need to set up some acceptance criteria. Okay, so this is how it behaves. If we give some input, so then it will kind of jump between the circles. Now, after all these jumps and all, how do we determine whether we consider this as a acceptance or rejection? So here the acceptance criteria is quite simple for this machine. So we accept a string if after reading all the input it comes back to this circle Q0, okay. We'll call this circle state. So now you can verify that these strings, so they are accepted. Why? So take simply 0, right? It starts from Q0, and if it sees 0, so it follows this arrow, right? So it comes back to Q0, and since this is the only input here, so that means okay, at the end of reading the input it is in Q0, so by our acceptance criteria here 0 is accepted, right? So take a slightly more complicated example. So this 1 1 0, right? So it starts from here, then it reads a input symbol 1, right? So it takes this path, right? So it jumps from circle Q0 to circle Q1. So we are talking about this input, right? So this so this symbol is kind of right. So next symbol is again 1, right? So since it's now in circle 0, okay, so it has to take this path back to this Q0. So it takes this path from here to here. So now this one is also processed, right? Then it takes the 0 as input, and since it is here, upon seeing 0, it again takes this path. Sorry. Finally it's in Q0. So that means this 110 is accepted. So similarly you can verify that for these strings, so these are not accepted. So if you start with Q0 and jump between circles depending on the symbols of these strings, so you will not come back to Q0, so that means these are not accepted. So this is just one example of what we mean by model of computation. So this is somehow in more detail showing how to compute the yes/no answer, right? And though we will not prove it here, and we will prove it much later, that this accepts strings which are binary representations of which are binary representations of integers divisible by 3. Okay, so binary representations of integers. So I hope all of you know what binary numbers are. So what are these numbers? So this 00 is actually the integer 0, so it's encoding the integer 0, right? So again this string 00 is encoding the natural number 0. Okay, so what this 11 is encoding in binary in form, so this is 3, again this is 0, this 000 is 0, this is again 3, and this is 0 0, sorry, 1 1 0 is, so this one is just 6, right? And here you can see you have 2, again this is 1, this is also 1, and this is also 2, 1, this is 4, right? And this is 5, sorry, this is 5, this 101. So all of these are not divisible by 3, and this is divisible by 3. So this machine is actually doing something useful. It is solving the computational problem that given any integer, find whether it's divisible by 3 or not. So that's a decision problem, and here we have converted it about a problem on formal language, and this is a model of computation which actually solves that problem. So now you see that this is a deterministic automata, because so when you are in this circle and if you see input symbol 0, so what will be the next step? So in the next step you will be in Q0. So there is no ambiguity about that. If you are in Q0, if you see this input 0, then you are in Q0. If you see 1, then you are in Q1. Similarly, for each circle, if you see 0 and if you see 1, so for this on 0 you take this, on 1 you take this, again here on 0 you take this, on 1 you take this. So at each step, the next step is fully determined by the input symbol. So this automata is actually a deterministic automata. Okay. Okay. So I already explained the transitions here. So again, here is another input. You can just pause and see how this input is accepted. So so once it reads this symbol, suppose it starts reading it from left and moves to right. So on this, it takes this transition. On this input, it takes this transition, and so on. So similarly, what we defined in the previous slide, the similar thing will also follow, and you will see that this will be accepted, because at the end it will be in Q0. Okay, so that was some deterministic behavior. Now again consider a similar this circle hopping machine. Okay, again it starts from Q0 and it reads the input one symbol at a time, and it follows this arrows accordingly. But now you see that if the current state is Q0, so if you are here and if the current symbol that you are seeing from the input, so if that is 0, okay, so then it can either take this path, or again, so this 0, 1 means both on 0 and 1 it can take this path. Okay, so if it says a 0, it can also take this path. If it says a 1, also it can take this path. So that means if it is in Q0 and if it says 0, it can either land here or it can come back here. So here is the non-determinism. You do not know whether in the next step whether it will be in Q0 or Q1 if your current state is Q0 and if your current symbol is 0, right? So now if we cannot predict how the machine will behave, if it can go this way or that way, then how are we going to decide whether the answer is yes or not? So in the previous example it was very simple. Everything was deterministic, and if it reaches Q0 then we say yes, otherwise we say no. Now the problem is, say we are just feeding this input 0 0, right? So one behavior could be that, okay, it first took this path on the first 0 and then it took this path. So after reading 0 0, it's in Q1. Another behavior could be that on the first 0 it took this path, this arrow, and then in the second 0 it takes this arrow. So now it is in Q0. Okay, so then how will we interpret? So here the acceptance criteria is that you need to consider all possible paths. Okay, and out of all these possible paths, so out of all the possible ways that it can reach a state after reading the entire input. Okay, so after reading the entire input, so it can reach multiple states, and you consider all possible ways it can reach some state. For example, here it can reach either Q1 or Q2. In fact, it can also reach Q0 because it can take this and again this, right? So you consider all this possible way, and out of that, if it, at least one of them is that it reaches Q0, so then you accept. So in that case, we accept 0 0 because this possible number of cases are 3, and out of those 3 cases, one case is this where it reaches actually Q2. So we say that 0 0 is accepted. Okay, so it's not that, okay, if the machine takes this path, then it is not accepted. If the machine takes this path, then it is accepted. No, for a particular run, if there are more than one possible way to run it, so for a particular run, you do not say that this thing is accepted or not. That you can do with deterministic version. So here you have to consider all the possible ways that it can take on that input, and out of all these possible ways, if there is at least one way to reach this Q2, then only you accept. So there will be strings for which there are no way to reach Q2, right? For example, this 0 1 0. So what will happen on 0? Again, after reading this first 0, it can be either in Q0 or Q1, right? So then it reads 1. So if it is in Q1, then it has nowhere to go. Okay, it is kind of stuck here. It can't move. So it cannot process the rest of the input. On the other hand, if on this 0, this input symbol, it took this path, okay, from Q0 to Q0 itself, then it has a chance to process this next one, because it will be in Q0. So on this one, it can again take this for this one. Okay, so again it will come back to Q0, and then it reads 0. So now it can again come back to either Q0 or Q1. So this possibilities. So either it takes this path first and then gets stuck at 1, or it takes this path for this 0. So then for this one, it will again come back to Q0, and for this Q0, it will go to either Q0 or Q1. But for all, these are all the possibilities, right? And out of all these possibilities, we cannot reach this Q2. Okay, it's not possible. So that is why this 0 1 0 is not accepted. So those were kind of examples of automata, a very specific kind of automata called finite automata. And also we gave the example without actually defining finite automata, but still I hope you got some idea about how what these mathematical computers look like. So another model of computation is grammar. Okay. And they are, as I mentioned before, grammatical rules as we have in natural languages. And this rules allows us to generate strings, as opposed to this automata model where you can think of it like a machine going through the strings one by one. So these grammars, on the other hand, they are rules to generate a set of strings. Okay, and the acceptance criteria, so this is the acceptance criteria here. The acceptance criteria is input string is accepted if and only if it can be generated. Okay, so again, this grammatical rules, so they allow us to generate a set of strings. That set can be infinitely large, it can be infinite or finite or whatever, it can be empty, but it will some set of strings, right? And if a string is in that set, if you can generate that string, then you say that that string is accepted, if and only if. And as we defined for this automata, the language accepted by this grammar is the set of all strings that it generates. So in general, for any model, if you remember in a few slides back, we defined this thing. So this language accepted by model M is the set of all strings that is accepted by M. So for grammar, acceptance means you can generate that string. So here this means the language is all the strings that is accepted or generated by the grammar. And then again, there are different kind of grammars, like regular grammar, context-free grammar, context sensitive and unrestricted. And each of these grammars actually correspond to this automata also. So these four and these four, they have one-to-one correspondence. Okay. So let's see an example of grammar. So this is a context-free grammar. So the rules look like this. So first of all, you have an alphabet over which the strings will be given, and the rules look like this. You have some symbol here, and on the right hand side again you have a mix of this symbol, this symbol from this alphabet and this other symbols which are not in this input alphabet. Okay. And the rule is this: you start with this S. Okay, you first write down, say, this S, and then use these rules. These are called production rules. So use one of these rules to generate new combinations, right? New strings, but these strings are over this symbol as well as this other symbols. So here I am using this rule 2 to replace this S by this combination. Okay. So then I am using rule 3 to replace S by this combination. So here only this S will be replaced, right? So these A's are already there in place. So if I now replace just this S by BSB, so then we get this. Again, by rule 2, we replace just this S, okay, with this combination. And say finally we use this rule 2 to replace this S with empty string. So all we get is a string, a string over this alphabet. So there is no capital S here. So once we get here, we have generated a string. Okay. And that means this string ABAABA is accepted by this grammar. and we consider all those strings that are accepted by, so that is the language accepted by the grammar. And if you cannot generate some string, so that means that is rejected. Okay.